Welcome everyone. This is the first international symposium of quantum computing and musical creativity. I am Paulo. I'm going to host the first paper session of this event. We have very interesting talks for this session. They are mainly about thinking about music composition, musical language in a quantum way. The first talk that we are going to have is from Karl Svozil. Hope that I'm pronouncing this right.
Yes.
And he's an associate professor from the Vienna University of Technology in Austria. And he's going to talk about conceptualizing quantum music. So let's all welcome Karl Svozil to the stage. And Karl, I think the stage is yours from now on.
Thank you very much. Thank you very much. Let me just tell you how this is an anecdote, how I came to quantum music. I was invited by Professor Dalla Chiara from Firenze to a workshop on quantum mechanics and art in 1913 already. And I said to myself, there isn't much said about, at that time, there wasn't much do about quantum music, so I said, why not do it? Because it's a new type of expression, and the topic is very pertinent to the conference, and this is how I started. And then I'm not very knowledgeable in the notation of music, and I have a good friend who understands music very well. And who is also a very good physicist. So I joined forces with Volkmar Putz, who is now at the University College of Teachers. And we wrote this paper that was published in 1917 in the conference proceeding to Professor Dalla Chiara's conference. And well, there are some anecdotes. For instance, let me tell you only this anecdote to the conference, because it relates to music. I'm a fan of Schönberg, you know, and of course everybody. And I said to Dalla Chiara, may I ask the daughter of Schönberg, who was there, Nono? May I ask Mrs. Nono why there was such a abrupt difference between the Gure Lieder and what Schönberg did afterwards, the 12th time music. And Marisa said, Karl, you will not ask the daughter of Schönberg this question. But she answered it in her independently. She answered it in her talk. You can ask me afterwards what she said. Okay, so there was following as a follow-up. There was another paper that just was published as a preprint. Kindly, Professor Miranda asked me to write up a second version, an improved version of the paper, which I hope we did, and it's hopefully will appear next year. So these are the two available sources of our thinking about quantum music. And basically, what I really want to talk about is the space of the realm of quantum music, the music expressibility that comes from the new expressibility of quantum mechanics. And I think this is what you asked me to talk about. I hope so, at least. So let's jumpstart with some basic features of quantum mechanics. There are a couple of basic features, and as in quantum computation, people might not agree in what is the most important or the most characteristic feature of this, but I will just mention a couple. Yeah? And one of the features is that if you compare quantum music to classical music is in terms of classical physical states based on Boolean algebras, on Z-theoretic intersections, Z-theoretic operations and relations, yeah, contained relation, intersection, power sets, and so on and so forth. Whereas quantum music is vector-based. Basically, since Dirac and von Neumann in the early previous century, we have developed a very nice conceptualization of quantization in terms of, let's say, pure states as vectors. So you're talking about vector spaces. And in order to derive frequencies, you need a scalar product. So you have a Hilbert space. And there the whole machinery goes on. You have a temporal evolution in particular, which is very important and very pertinent to the topic, that is in the form of permutations. So generalized permutations that it is a one-to-one modulation. In quantum mechanics, one calls this unitary transformations, but it's basically just generalized permutations of these vectors, generalized rotations of these vectors in complex Hilbert space. So what are the particular features that are pertinent in our case? First of all, it's parallelization. Through the coherent superposition, mathematicians like to call that linear combinations of classically mutually exclusive tones or signals that are acoustic. Yeah. So basically, if for instance, in classical physics, a particular a tone is allowed and another one is disallowed, you can have it both in quantum music. And in a very new specific way that is not just cohabitation, you know, it's cohabitation not in configuration space, but in Hilbert space. This makes everything very different. And one has to contemplate a little bit over that in order to understand that, you know. And then there's this new feature of entanglement that was realized by von Neumann and Schrödinger, of course. Schrödinger coined that term entanglement, which describes a kind of correlation, but unlike classical correlations, quantum entanglement is characterized by a kind of scrambling of information, of if you want to have it, classical information into relational information among multiple bits. So that the individual particles or individual tones lose their individuality. They lose their definiteness. Yeah, and all that you get is the information is now contained in relational information. Let's say if one particle, let's say one tone is one way and the other is a different way, then this is classically still allowed and you have this correlation. But in quantum mechanics, entanglement describes that none of these particles have a definite state, but the joint state, from the joint state, you know that if the particle is in one state, the other particle has to be in another state. That's the modulo de phase characterizing the Bell state, for instance. So these are very important differences, and one has to realize that it's not only the correlation, but it's also this loss of individuality of the original tones that is very important here. And you can see there's a sort of zero-sum game due to this unitary transformation, which is just a permutation. So you cannot gain something, you have also to lose something. You know, this is characteristic also for quantum computation, that it's not only you don't only get the goodies, you have also some disadvantages to cope with, and you have to very cleverly use the goodies, you know, in order to really get hold of the power of quantum computation, and in this case of quantum music. And of course, there's a second. There are other other very important properties of quantum information involving complementarity. That is, if you see one complementary thing with respect to the other. You can have it value definite, but then you don't have value definiteness of the other, and vice versa. This is a very interesting concept that has been developed by Pauli at that time in Switzerland already. And you have what is called contextuality, which has many definitions, but I would prefer, but this is my, little petty definition. I would have it according to the Cauchy-Specker theorem, rather as emphasizing the incapacity to embed quantum observables in a classical world. Yeah, but most of the people talk about contextuality as that the quantum frequencies, let's say in Clauser-Shimoni-Holt inequalities, are different from classical expectations. So there is a little bit of a discussion going on what is to be considered as contextuality. But this is, we have not really implemented that yet. So this is up to further research, one may say. Well, and then one could make a straightforward implementation. One can say, let's say that the octave, one octave one can encode into a Cartesian standard basis of 7-dimensional complex Hilbert space, and the basis elements are just the standard vectors. And then one can say that a pure tone, a pure quantum musical state, is represented as a unit vector, which is a mixture of these. It's very different from cohabitation, from a, this is really a mixture. This is really a mixture of these genuine states. And in order to be normalized, one has to normalize the coefficients. And then in musical composition, and actually any succession of quantized tones forming a melody, under quotes, would be obtained by successive unitary permutations of the state psi, a rotation in Hilbert space. And the realm of such compositions would be just the unitary group, the unitary, all unitary transformations. There's a very nice book that parameterizes this. This is by well, it slipped out of my mind. It slipped by Merneken, the unitary and the rotation group. It's a very nice book parameterizing these realms with these octaves and more general unitary, finite dimensional unitary transformations. Now, one may ask then, what is the classical perception of quantum parallelism? Because the rules of quantum mechanics disallow you to see the entire state as it is. If you think of that in a Platonistic universe, you would say, I cannot fetch direct. I have no access to the state vector directly, but I can make measurements, and these measurements boil down to a reduction of that probably parallelized states into the classical states, if I'm a classical observer. Now, this is an age-old debate. I will not touch on that one. How can this be? But as a matter of fact, actually, that means that different classical observers will perceive one and the same state very differently. So for instance, we give a little example. If you get a little composition of, let's say, two tones, mediated by this NOT gate that Mermin calls that an X. He has a very nice introduction to quantum computing science. For the non-physicists, which I highly recommend, it's also available on the net at Cornell, and he calls that NOT operator the X. Of course, it exchanges everything. And then you would ask, well, let's say you have 4 types of observers. The first type, here's the nodes C and G with a certain percentage. In that case, 40, almost 41%. And then you have G and C. So that's the inverse. That is heard approximately 13% of the time. And then you have CC and GG that have 23% of listeners. So there is this one can call funny or interesting situation. And this was on the basis of the first protocols of quantum communication and of quantum cryptography. Wisner's protocol was that you can encode a message, 2 messages at the same time, so that the listener has to decide what to hear. You know, it has to decide what to hear. That's a very interesting parallel situation. And then there is, of course, quantum entanglement, but I refrain from going deeply into that. I will just show you 2 pictures of the publications and kindly ask you to please have a look at those publications. We try to kind of formalize or make an inroad into quantum entanglement, musical compositions also, but I don't have the time to go too deep into that. So let me, and this is almost my last slide. Let me just tell you that, in my opinion, there is a trade-off between quantum versus classical music, and how should one cope with that? I truly believe that quantum music presents a novel form of musical expressibility and tonal forms. So it largely, very largely increases our ability to express ourselves in musical terms. There is the perception of this new form is interesting. Is an interesting subject on its own, For instance, there exist papers saying that we are capable of perceiving 1 photon. This has been this was, I believe, a Nature paper from a lab in Vienna even. So this is an interesting subject. Perception of quantum music is interesting, but also, of course, this huge realm that quantum physics opens us for artistic, in general, expressibility, because this is of course not only restricted to musical expression. It's also to light in its various forms in quantum optics. And one has also to say or to accept that quantum music lacks some classical forms of musical expressibility. Yeah, because everything, if you stick to the domain of quantum music proper, all is 1-to-1. All is a kind of generalized permutation, and getting rid of tones is very difficult. In such a situation, you cannot lose the tones. You have to transfer them to a different regime somehow. You might need more space for doing that. This is, of course, solvable, but it's also a matter that needs to be addressed. And for instance, just as the halting state, there's the issue of, is there a halting state in quantum computation? There is no silencio, there is no total silence, this is, but total silence, I'm a Mahler fan, total silence is a very, very important asset. And one has to cope with the situation that one has to define silence in a very different way in quantum computation. So these are just examples, you know, that we are just starting up to think about these things and need to think harder. And so the world is opening up, you know, this is the good message. Yeah. And with this very optimistic prognosis, I thank you for your attention, and I stop here.
Thank you very much, Karl. That was a very interesting talk. If you have any questions for Karl, we have the Q&A section. You can ask them, and I will filter some questions to ask. I actually have, as we wait, I have some comments. I really liked your presentation, and I just separated some keywords that I thought were interesting, like the loss of individuality of notes. This concept really caught me, because it really summarizes the way that entanglement happens, and it's really interesting to think aesthetically, how can this translate to music thinking, right?
Yes, exactly. Yeah. I mean, the whole story started actually with Schrödinger's famous article über den gegenwärtigen Zustand der Quantenmechanik, you know, where this was his programmatic series of papers, and he wrote about that. And there's a very nice article by Zeilinger on foundational principles, where he said one of the foundational principles is that you can encode, let's say, in an n-partite system, you can encode only a finite amount of information, which means that if you relationally encode something, you have to lose something on the other end. And this is from a formal point of view, it's quite straightforward, because it's the unitary transformation, you know.
Great. So I'm going to read. We have some questions from the Q&A section. Well, the first question is actually a simple one. There is Sunil is asking again for the book reference that you talked.
About the Merneken, the unitary and the unitary and orthogonal group. It's called Merneken. It's a little booklet that parameterizes the orthogonal and the unitary transformations in n-dimensional Hilbert space. So this is a technical book which is extremely interesting to read. It's the main idea, as far as I got it, is the following: you can, for good, parameterize in 2 dimensions the orthogonal group and the unitary group. And of course, also the permutation matrices. You know, this is there's a degree of downgrading. You first have the unitary transformation, then the orthogonal, and then the permutation matrices. And so you can do that for good in 2 dimensions, and then you attempt to characterize a complete parameterization of all these transformations by just concatenating transformations in 2 dimensions, yeah, in 2-dimensional subspaces. This is the main idea of the book, and the main technical approach that is carried out there, as far as I understand.
Oh, that sure is a very interesting read. We have another question from Nikitika. She's asking, you mentioned basis for the notes of an octave. Wouldn't there be a preferred basis where other bases are dissonance, meaning frequencies are maybe thinking about harmony and how these quantum bases are related? Yeah,
I truly believe that there is probably one, if you like it, but this is a wild world open, you know. You can, I think you can have all kinds of bases. You can have non-orthogonal bases, or if you talk about normalized vectors, non-orthonormal bases. you can have all kinds of things. Physicists usually stop at the Cartesian standard basis, but this is just one basis that is taken arbitrarily, and the components of that basis are usually taken as the vector, you know. So we have mathematicians here at the TU, you know, who say, you know, because I give some mathematical lectures to the introductory letters and the lectures, and they say, well, you should always say, well, this is a component relative to that particular basis, you know. But there exist zillions, I mean, a continuity of bases in Hilbert space, and you can do all kinds of very interesting basis changes. It's from a formal point of view, it's well worked out, but one has to just apply that to this new domain. Great.
I also have a comment from James Weaver that he's just having having a note of appreciation for your paper that helped pave the way for folks like him to think about quantum music. So it's really
thank you.
Great thanks. Maybe we can have one more question. Okay, from Marcus, what about something similar to the vacuum state as silence?
Yes. So we are in that respect, yes, true. So we are entering quantum field theory here. And I didn't, in the paper, there's a little bit on that. There are some sections on that also. It's not very well probably said out loud, but actually if you enter multipartite configurations, you know, you have modes then of music, and these modes can be filled with 0 photons and so on and so forth. But then you have also the 0 point fluctuations, all kinds of things come in. But yes. I mean, one can always define a state to be, one can always define a state to be the silencio state. And if you have only that state, you have, I guess, because it's unitary transformations, you might only have it for a short period, you know, and then change it again and then come back again. This is also possible, but there is no permanence, you know, like halting, and from that time on ever since. And previously there was richness in the composition, you know, so because it's just a unitary transformation. The metaphor here is a unitary transformation. It's a kind, the metaphor that is in my mind is a permutation, actually, a generalized permutation.
Okay, that's great. I think that's it. We are going to follow up to the next talk. I would like to thank Karl for his great talk about conceptualizing, about how to think about physical concepts in a musical way, and how this will impact the new quantum serialism movement, probably in the next few years. So now we are going to follow to the next talk.